Our last bit of differentiation then is using it for problems. So here, a bin is made of metal of negligible thickness into a cylinder closed at one end. It's required to have a volume of 3,000 centimeters cubed. If A is the surface area, show that A equals pi r squared plus 6,000 over r. Now, most of these questions will be something to do with volumes and areas of shapes. If it's anything more complicated than a cylinder, you'll be given the formulas, but you're expected to know your formulas for a cylinder. So this is back to GCSE. The volume is pi r squared h. The curved surface area, so that's like your label on your tin, is 2 pi r h. And then if you've got a base, it's just a circle, so it's pi r squared. And if you've got the top, that's also just a circle, so it's pi r squared. In this case, obviously, we don't have the top. Okay, so we're given two things. We're given the volume and asked about the area. You could also be given the area and asked about the volume. So we know that the volume of the cylinder is pi r squared h, and we're told that the volume has to be 3,000. The area then, we're told there's just a base, so that's pi r squared, plus the curved bit, which is 2 pi r h. We've got no top on the bin. So what we're trying to prove doesn't have a h in it. So what we want to do is use our formula for volume to rearrange that to get h in terms of r. So 3,000 over pi r squared would be h. So we're going to substitute that into our area formula, okay? So pi r squared stays the way it is. 2 pi r times h, which is 3,000 over pi r squared. So again, the first bit staying the way it is. Hopefully you can see, well, we can cancel a pi here and a pi here. We can cancel one of the r's on the bottom with the one on the top. So we're left with 2 times 3,000, which is 6,000. And we just have r on the bottom. And that's what we were asked to prove. Next part of the question then, if the amount of metal required is to be a minimum, find the radius and then the required area. So this is our key word here, minimum. Could be maximum as well as minimum in this case. So we're looking at the area. I'm just going to write it as pi r squared plus 6,000 r to the minus 1, bringing that r up to the top. So when I differentiate, okay, so you see minimum, that should be your clue to differentiate. Remember, pi is just a number, so it's 2 pi r when we differentiate pi r squared minus 6,000 r to the power minus 2. So it's a minimum, so it's a turning point. So I'm going to let that equal 0. I'm going to bring my r back down. So it's 0 equals 2 pi r minus 6,000 over r squared. Bringing that 6,000 over r squared across, we get rid of the minus. Now I'm going to bring the 2 pi across and divide by it. And I'm going to bring the r squared across, and we get r times r squared, which is r cubed. So that means r is the cube root of 6,000 over 2 pi. And remember, we should be given things to 3 significant figures if we need to. So it turns out to be 9.85. Now, even though the question doesn't ask, you have to prove that it's a minimum. So to do that, we're going to differentiate again to get d2a by dr squared. So 2 pi r, differentiate that, we'll get 2 pi, and that's going to be plus 12,000 r to the minus 3. When we put in our value of 9.85 for r, it turns out to be 6 pi when r equals 9.85. So therefore it's greater than naught, which means it's a minimum. Okay, so this is a really important bit that you remember to do. Sometimes it asks you, sometimes it doesn't. You always have to prove that it's a minimum or prove that it's a maximum. So we've got the radius, we've proved that a minimum. We also need to find the required area. So we need to put a value for r back into A to get what it is. A then is pi r squared plus 6,000 over r. So that's pi times 9.85 squared plus 6,000 over 9.85. You should, now I'm writing 9.85, but I've kept the full answer on my calculator screen. You shouldn't be writing up to the very end. So we get 913.9. So it's 914 centimeters squared to 3 significant figures. Our second one then, an older question that used to be on a non-calculator paper. So you used to have to do these questions without a calculator. So the solid object consists of a cylinder of height h and radius r surmounted by a hemisphere of the same radius. Surmounted just means they're attached together. If the total surface area S is 20 pi, show that V equals this. And the formulas that you would be given would be the volume of the sphere and the area of a sphere. Obviously a hemisphere then would be half of that. Okay, so again we're dealing with volume and area. So our area, we'll have the base of the cylinder plus the curved area of the cylinder plus then the hemisphere. So if a sphere is 4 pi r squared, then a hemisphere is 2 pi r squared. So that means 3 pi r squared plus 2 pi r h. We're told that the area is 20 pi. And hopefully you can see that pi can be cancelled out. So we have 20 equals 3r squared plus 2rh. Then the volume of the cylinder is pi r squared h. The volume of a sphere is 4/3 pi r cubed. So a hemisphere is 2/3 pi r cubed. Now the formula that we're looking to get has no h in it. So we're going to have to rearrange the area one here. So bring the 3r squared across and take it away. That equals 2rh, which means h is 20 minus 3r squared over 2r. So we're going to substitute that into our formula for V. So it's 20 minus 3r squared over 2r. And that's plus 2/3 pi r cubed. So we can cancel the r down here with one of them up here. And then I'm going to multiply in. So I have 20 pi r minus 3 pi r cubed all over 2 plus 2/3 pi r cubed. So separating out this first fraction with 20 pi r over 2 minus 3 over 2 pi r cubed. So that gives us 10 pi r. And then we've got minus 3 over 2 pi r cubed plus 2/3 pi r cubed. And when you work that out, you get minus 5/6 pi r cubed, which is what we were looking for. The second part of the question, then find the value of r, which makes V maximum, and calculate the maximum volume given your answer in terms of pi. Again, there's your key word maximum, so you know it's got something to do with differentiation. So V was 10 pi r minus 5/6 pi r cubed. So we're going to differentiate V with respect to R. So remember, pi is just a number. So 10 pi R, when we differentiate, we just get 10 pi. Minus 3 times 5 over 6 is 5 over 2 pi R squared. That's going to equal 0 for a maximum. Bring the minus 5 over 2 pi R squared across. And cancel the pi's. So R squared would be 10 divided by 5 over 2. So that's 4, which gives us a value of R as 2. Again, even though it doesn't tell you, you have to prove that it's maximum. So d2v by dr squared. Differentiate 10 pi. Remember, that's just a number, so it disappears. Minus 5 pi r is what we'd get. When r is 2, d2v by dr squared would give you minus 5 times pi times 2. That's minus 10 pi. That's going to be less than 0. Therefore, it's a maximum. And then it asks you to find the volume. So 10 times pi times 2 minus 5 over 6 times pi times 2 cubed, which is 8. And it tells you to leave your answer in terms of pi. Okay, so that's how you can tell. It's one of the old questions that you're not asked for 3 significant figures. You have to do this without a calculator. So we've got 20 pi, and that's going to be 20 over 3 pi. And that gives us 40 over 3 pi. Now, there was no units in the question. If there had been units of centimetres, we'd put centimetres squared, centimetres cubed. If it mentioned anything to do with centimetres, R would be centimetres, and our volume would be centimetres cubed. If it had been metres, then it would be metres and metres cubed, and so on.